Master arrives. There we go.
Okay. So, yeah, I'm going to be presenting some of the work we've been doing at the University of Manchester, looking at the continuous core thin sections from 73002. And we've been looking at using ChemScan to try and find some exogenously derived components that might be within these core samples. Because cores like 73002 are really important because they potentially provide insights into the bombardment history of the lunar surface, and in turn they might preserve a record of some meteoritic materials that may have been transferring through the solar system, and that can tell us a lot about the bombardment history of the moon. So in the past, searching for meteoritic fragments has been quite a manual process, taking a lot of time to really in detail go through each thin sections like these and try and find minerals and class of potential interest. So what we've tried to do is to use ChemScan, which is a quantitative evaluation of materials by scanning electron microscopy, to produce mineral phase maps, and this allows for a much more rapid identification of minerals that have potentially non-lunar compositions that then we can go and investigate further with other processes such as EPMA. Bigger. So the project aims can really be sort of summarized with this sort of flow diagram. So we get the samples and we put them in the scan electron microscope, which the ChemScan runs alongside with. We get these mineral phase maps, and then we use the ChemScan software to highlight minerals of interest, and these are minerals that we would commonly find in meteorites. And then we would use that to go and select some class that look potentially interesting, inspect these class manually a little bit further, and then move on to some EPMA analysis. And then, the idea being that we'd find meteorites. I like those ambitious and put plural there as well. There we go, that's the right one. So just a bit of background for ChemScan, because I realise not everybody will necessarily be familiar with the technique. So as I said previously, it runs alongside a scanning electron microscope. You set the step size for the scan of your sample, and this is essentially the pixel size in the resulting map. So for all these scans, we did 5 micron step size. And so at each point, the system takes an EDS point and it takes backscatter brightness, and it'll use these measured data to compare it to a SIP list, which is a species identification protocol list. Essentially, this is a big mineral database of various different mineral definitions. And so it'll go through the sample, and each pixel will be matched to a mineral definition. That mineral has an associated color. And as you can imagine, it builds up gradually a picture of the minerals in your sample. And this is just an example of a polar 15 Mare basalt, just to show that it picks up zoning and all different textural features as well as the mineralogy. So here's a scan of 6011. I should mention that these have been processed using a lunar specific mineral list. ChemScan's originally designed for the mining industry, so as you can imagine, there's a lot of minerals in their predefined list that aren't really essential or applicable to lunar samples. So we removed a lot of those, and then was really able to go in and tailor a lot of the compositions specifically to lunar samples. Especially, we did a lot of work on the glass compositions in particular. So once we've got our nice mineral map, if I just flick back to that one, we then want to be able to highlight these potential meteorite class. So to do that, we use the system to highlight some minerals that are commonly found in meteorites. And we do this with a secondary list. So as you can see with the legend at the bottom there, we've essentially just stripped back and dumped most of the minerals into other minerals category. And we've just pulling out some of the key phases that we're potentially interested in. So just to get your eye, and you might probably be able to see some red specks there that are some iron associated phases. And we've also got, probably see the bigger green splodges of high phosphorite olivine in there as well. Now, the caveat of all this is that these minerals are all commonly found in lunar samples as well. So they just by highlighting the class doesn't mean that it's chock full of meteorites. So what we had to do is then go and inspect some of these classes in a bit more detail. So we had a first pass through just looking at the meteorite mineral list just to see whether we could immediately identify some of these classes as lunar lithologies. After that, we were sort of dug a little bit deeper and was able to use the full lunar mineral list to sort of flick between the two and get an idea of some of the other phases present within these classes. The ChemScan also, you can extract element maps, so they were really useful in flicking between all the different maps at the same time. And then after that, we identified some class that we were really wanting to get a bit of a closer, more detailed look at, and we went back on the SEM and just took some high resolution backscatter images. So from this, we narrowed it down to 33 classes that we wanted to take forward to get some probe analysis done to really see if we could tell something about the composition and where these classes originated. So in terms of what we looked out for, so these classes either had highly magnesium mafic phases, that were either metal or sulfide rich, had albitic plagioclase compositions, or had chondrule-like mineral textures. So all these things that could indicate that these are meteoritic in origin. So the analysis here is just shown for pyroxene and olivine, but we also performed the analysis on metal and sulfide phases as well. So we just got a pyroxene plot where with 73002 in the purple color, and then some other Apollo data just for reference there as well. And then we've got the olivine data. You can see we had quite a spread from down to phosphorate 19 up to phosphorate 96 with the olivine. So in terms of plots that we use to really interrogate the probe data in terms of whether we thought they were lunar in composition or not, was these iron versus manganese plots. So all the data from the 73002 is in the yellow circles, and we've got polar samples and lunar meteorite values in the blue colors. And then you can see on there, we've got some trend lines for different planetary bodies, like Mars, Earth, ordinary chondrites, and the moon. And unfortunately, you'll see most of these plot along the moon line or within the spread of other Apollo samples and lunar meteorite values. So to sort of summarize what we found in terms of meteorites, we didn't find any. Everything that all the classes that we identified and took for probe analysis, we think are of lunar origin. But this level of sort of detailed investigation of these thin sections was really useful because it highlighted some interesting clasts and textures, which I'm sure we'll hear a lot more details about these in some of the talks this week. But in terms of what we found, just a quick overview, we had some magnesium sweet fragments that had these really high phosphorite values of 94 to 96. We found lots of different interesting impact melts with different textures, a lot of metallic rich textures as well. Also some alkali sweet material on the top right there, and some really interesting sulfide intergraphs just on the bottom right hand side there. I think I've gone through that really fast, which probably helped with the start. So to summarize, ChemScan is really useful, non-destructive method. We collected a wealth of data. There's a lot more still that we can use the data from these scans to do. But here we've shown that the ChemScan software can be used to rapidly identify potential class of exogenously derived components. And it was a much quicker method than having to manually identify some of these class in the thin sections to start with. And in future, we're hoping to have a look and use this method on 73001 continuous core sections. So yeah, hopefully we might have a little bit more luck with those. But just really like to acknowledge the curators at JSC, because these thin sections are amazing. Just the images there that sort of speaks to that, and acknowledge the Travel Award for making it possible to come and present today. Thank you.